Thank you very much for having me here, and thanks for the nice introduction. I was never linked to that movie before. Probably also not so soon again, but so I have to enjoy it now. So who of you have worked on something that has to do with steganography in the past? Some of you. That's quite surprising. Usually I talk to people who hear the word for the first time, but I introduce it very briefly. So I have two examples here, pictures from Wikipedia. On the left side, we have the classical image hiding scenario. So the cat of the picture is hidden in the image of the tree. And the 20 euro note has a watermark. That's two forms of information hiding. But in general, we try to hide something in something else. And this something that we hide can be basically everything. It can be code, it can be images, text, it can be multimedia data. It can also be any form of raw data. So it's up to us what we hide. And the thing is, in what can we hide it? Well, that list also gets longer and longer. We can hide data in text and code, in multimedia files, in executables, in network flows and blockchains. Recently, someone did that. Metadata of basically everything, like file systems and cyber-physical systems. I will pick two of these fields, network flow data and cyber-physical systems. So first I will speak about the introduction, the fundamentals for a few minutes of steganography and information hiding. Then I will explain how it's done in these two domains. So in general, what we have to do in steganography is try to look like something else. So we hide a message in some object, and the object should look like something else. That's done in nature as well, and called mimicry. And the idea is that some predator cannot decide between some prey and a not prey object. So can I eat it or can't I? And animals try to look like something else so that their predators cannot detect that they are in their reach for an attack. During history, I don't go into all these details, but in ancient Greece, development and application of steganography already started. So people were hiding messages on human skin using tattoos. Later they hid data in musical compositions, and during the World Wars, these technologies emerged quite well, and a lot of development time was dedicated to fool the enemies. So, but in the 1980s, that started to become digital. People started to hide data in image files and audio files and so on. And then in the late 80s, the first approaches were published where data was actually hidden in network transmissions. So nowadays we have a few more domains. I already listed them, and more domains are discovered. In comparison to the historic application of steganography, where someone had to carry each steganographic object, each cover object, to the receiver separately, we can now have a constant transfer of steganographic data over the network. And that allows us to hide much more data and in a constant manner. That also means that it's less pricey. When we look at the basic taxonomy, I will speak about steganography and covert channels. There are also other domains like anonymity research and watermarking, but I won't focus on them. I will focus on covert channels and steganography. But what's the difference between these two? Well, a covert channel, actually the term is already also from the early 70s, means that we have some kind of a communication channel that is not intended to be there and used for communication purposes. The early covert channels were found on operating systems and were not used in the network scenario. And the standard scenario for covert channel application is that we have two people in jail. It's called the prisoner's problem. So Alice and Bob are in jail, and they want to exchange information about an escape plan. But the only way to communicate is via the warden, Walter. So they have to give Walter their messages. Walter can look at them, analyze them. And if they write, okay, let's escape then and then he will most likely not deliver the message. So what they try to do is they hide their message in some object and hope that the Walter does not see it. And we call that object in which we hide the data a covert object, and the steganogram is the secret message that we transfer. So we have a little bit of more terminology. I don't want to bore you with the details, but you can also apply keys similarly to cryptography. And we say that we embed a secret message in a cover object and then we extract it. So now back to the warden. The warden can have different capabilities. So if you apply steganography, the warden can either try to just detect that there is steganographic communication at all. That's called a passive warden, or he tries to detect that somebody else is involved in it. That's still passive. But he can also be active. That means that he can modify your messages and then tries to remove your messages from the cover objects. If he is malicious, then he can also spoof the messages to influence the covert communication. That's the most sophisticated version of the warden. So the question is it applied in practice? Yes. There's certain malware that applies steganography, and steganography involves the covert channel creation process. So we have that in the wild, and it's increasingly used. So if you would like to see a summary, I put 2 links there to summaries. However, what they do is basically letting their traffic appear like it is something else, like messenger traffic or SSH traffic or something, and they hide the data in this kind of traffic. We funded Europol-supported initiative called CUING, Criminal Use of Information Hiding, to track what is actually happening in that domain, and also to share knowledge about steganography. So if you're interested, let me know, and maybe you want to join. However, besides of that malware scenario, there are also other application domains. For instance, in APT, you can use a steganographic communication to have a stealthy data exfiltration. I think today is also one talk on the agenda that has the focus on the data exfiltration. Then we have criminals who share secret information, like child pornography, what happened several cases in the several times in the past. Malware already mentioned, then secret services, of course, but there are also positive sides of the steganography application, like citizens that can use it to exchange their views in a way that is not surveyed, detected by the government, or journalists who want to express their opinion in a free way, so that the government does not restrict them with censorship. Okay, so in network information hiding, we have basically 2 domains. If we focus on what we actually hide, then we can hide the identity of communicating parties. That would be anonymity techniques. We can also try to hide the content of a communication. That's done with cryptography. But in information hiding, we either try to hide the fact that the communication is going on at all, or we hide the characteristics. That's called traffic obfuscation. So if we try to hide that the communication, that the secret communication is taking place at all, then that's network steganography. And this is what the talk is also focusing on. So how can we describe the techniques that are used to transfer data over the network in a secret way? Well, the problem is there are hundreds of techniques that we knew already since ages, and more techniques are developed. It's impossible to mention them all in such a talk, and it's also not useful to focus on every single technique. So what we did is we looked at everything that was published since the late 80s. We surveyed it, we categorized it, and we concluded that there are many similarities. Some techniques have just different names, but do basically the same thing. And we came up with a list of quite few patterns that describe the basic idea that these hiding tactics apply. So if you understand these patterns, you already understood hundreds of academic publications, core ideas at least, of the last decades. And I will show you these patterns now. This is the basic pattern taxonomy. Don't worry, it's actually quite easy, and I will go step by step through it. There are some newer versions of this, but I focus on the 2015 published version because it contains the most fundamental patterns. And in the meantime, we just have like 3 new. So you don't need to worry about that. We split them. So the covert channel techniques, we split the covert channel techniques in those that are influencing the timing of data transfers and those that influence the storage or the data that is actually transferred. Because these two separations were already proposed in the early 80s by the DoD and are the general distinction of covert channel techniques, so that we kept them. We also distinguish whether we modify some metadata, some non-payload of the network traffic or the payload itself. I exclude this part. That's digital media steganography, so you can select every media type and modify it. That's no news. But I want to speak more about the network side, so we exclude that. And if we exclude metadata, then we can keep the structure of the metadata or we modify it. That's basically it. So we came up with these 11 patterns, plus a few, as you can see, sub-patterns, special types of the patterns. And I will now go through them, starting with the one in the lower left corner, to show you how easy it actually is to hide data. So the size modulation pattern basically uses the size of network data that we transfer, network packets, and changes the size, like, for instance, by adding additional data to the payload. And then a larger packet can encode a 0 and a smaller packet a 1. So it's basically easy. If you add some error correcting and detection, then it's also reliable. Large packet means one symbol, small packet another one. You can also have multiple packet sizes, so you can encode more data per packet. Then we have the sequence pattern. Here we modify the order of elements, the sequence of elements in the metadata. So for instance, here we have one example that is a standard HTTP 1.1 request. In one case, we first send the user agent and then the accept language line, and in the other case, we flip it. This way we can signal different covert signals. Works well, was I think already proposed in 2006 or so. So all that I show you here is, in terms of these patterns, is work done by several people. You find it in the references. Then we have the add redundancy pattern. Add redundancy means we just add something that is not absolutely necessary. For instance, we can add the user agent or other header parts, but we don't have to. And we can also use that to encode the hidden message. And of course, you can, instead of using one line, you can add multiple of these header lines, and you can also do this just for selected packets, etc. There are plenty of ways to do that. Also, one idea that I really liked was to create a new IP version 6 destination option. That's also a form of this add redundancy pattern. Then there's PDU corruption. PDU, the protocol data unit. So if you transfer network data, you have usually something like a checksum. And you can somehow detect whether the data that arrives at the recipient is corrupted or not. But if you corrupt by intention, then you can also use the corruption, packet corruption, to signal hidden information. Of course, you will say now, yeah, we also have regularly occurring data corruptions because of the noise on the network, but here again, you need some form of error correcting or detecting codes. Then random value pattern, that is quite easy to understand because several protocols have some random field, like the IP identifier, or at least pseudo-random. You put some other pseudo-random number in it, and that's it. And several protocols like the IP version 4 identifier, the TCP ISN, or the XID field of DHCP have such fields that you can utilize for that. However, you maybe want to make sure that the distribution of your values matches the general distribution of these values for the protocol. Then there's value modulation. In that case, this is a little bit special because we have to select one out of n allowed values. So it's not a random field. We cannot write in the field whatever we want. It's some kind of metadata that follows a structured design, and we have to adjust to that. So we cannot use every value that we want. But for instance, in a simple scenario, you can switch between upper and lower case for non-case sensitive network protocols like this HTTP request. So where the uppercase letter indicates a covert 0-bit and the lowercase letter indicates a covert 1-bit. You can also use the TTL of IP version 4 or the backnet message type or similar values. So it's not necessary that you use some plaintext protocol for that. Or the destination IP address in a network where n hosts are located and you just don't want to send it to some host that just does not exist in a network because it's an anomaly itself. However, also this would be a slight anomaly if you have this kind of user agent with a mix of lower and uppercase characters. Several protocols have unused or reserved field. If you look into the RFCs, you find plenty of them. And you can also write some data in these fields. Traffic normalization may destroy your data, but at least you can try. And however, this is it's an easy to use pattern, but it's also one that is recognizable by many countermeasures. So most IDSs just detect that. If you set the IP reserved flag and you snort, then it's very likely that you have a rule that detects that. However, there are more sophisticated ways. Okay, that's it for the storage patterns. I now show you how you can modify timing behavior of network data to also encode hidden messages. The standard approach, or the one that is used the most, is the interarrival time modification. So if you over time send your network packets with a different time gap in between, you can use the time gaps to encode also different hidden bits, and that works also very well. However, you have to make sure that the values are not so small that the noise on the network influences you too much. You can do something similar with the throughput of your data. So you send a burst traffic for a short period of time, indicates 1 bit. If you send your data at a low rate, you indicate another bit. Also, you can do this stepwise, so you can signal more information per time. This is like the little brother of the interarrival time modification that we had before. Then, second last pattern, PDU order corruption, PDU order pattern. So many protocols have a sequence number, like the authentication header or TCP, and if the values here should indicate the sequence number. So we can mix packets because, and this reflects a normal behavior in networks because, as you know, IP packets can take different routes, so packet order maybe mixes up. This is why we have TCP to sort the packets at the receiver side, but we can also artificially jumble the packet orders, and then the sequence in which they arrive at the receiver indicate the hidden message. By the way, all the figures are from our book on the network information hiding topic. So last pattern is the retransmission pattern. The retransmission pattern forces a retransmission either at the receiver side or something or by the sender side. So in that figure, we see that the packet with the number 2 was sent twice. We just cause an artificial retransmission. Packets are retransmitted all the time because they got lost. So we can do this also for steganographic purposes. Also, the receiver can cause a retransmission at the sender side, but just not acknowledging a packet, and then the sender has to send the packet again, but the non-acknowledgement reflects the hidden information. So it's I send data to someone, and someone tells me, okay, this is a 0 and this is a 1, by not acknowledging my data. Looking at what was published so far, we can see that some patterns dominate, while others were almost not used. The reserved unused pattern, value modulation, and redundancy pattern were used the most. While, for instance, the retransmission pattern, we had 2 or 3 examples that we found. Okay, so I have a challenge for you. Actually, I have 3, but this is the first. Because you are hackers and you like challenges. So the first challenge is do not find a new technique for hiding data, but find a new pattern. If you find a new pattern, you find you have developed a completely new idea. More creative input is necessary for that, but if you find a completely new way how to hide data that is not reflected by the existing patterns, well, then you did something very interesting, and most likely you can present it on a conference like this. If you found one, we developed a unified description method, and that is tailored so that you describe all the relevant aspects of it. It's easy to use. And why should you use it? Because it allows you to communicate your ideas in a way that everybody understands them. That also will make your work maybe more appreciated, because a lot of the papers on information hiding are very, very technical. But if you describe the hiding techniques in a structured way, it's easier for everybody. You can also use it to describe a new hiding technique if you don't found a pattern, but it works for both. Okay, so besides of these basic hiding techniques, there are also very sophisticated methods on top of these hiding patterns. One is microprotocols. The idea is we've put a protocol into the covert channel, and that enriches the functionality of the covert channel a lot. We did lots of stuff in recent years, like building up covert channel overlay networks, doing dynamic routing on overlay networks to bypass firewalls and stuff like that. You can transfer firmware upgrades for systems that run your covert channel software, for instance, as a covert channel proxy or covert channel router. Of course, you can have the error correction and detection in it. There's a lot of stuff you can do. Then there's pattern combination. So instead of using one pattern, you can combine them. Let's say you modify packet size plus interarrival time. Then you have a pattern combination. And you can basically combine all patterns. You can also do this in a multi-layer fashion. So maybe one pattern influences the TCP header, another one the IP header. It depends on you. and pattern hopping. Pattern hopping means we randomly select one pattern per packet that we send, or per flow, or however we want to do it, and then we switch. This has several advantages. For instance, if one technique gets blocked, the others still work. If one gets detected, the others may still remain undetected. Okay, challenge 2. Find new countermeasures. Because it's a challenging thing to find a good countermeasure. There are some good ones. You can either detect, you can limit, or you can prevent such a covert channel. But the big problem is there are so many. So what I think is necessary are pattern-based countermeasures and not countermeasures that focus only on single techniques. Some people started to working on that, but there's lots of works that still can be done. Okay, so that's for the network information hiding part. I also want to show you some very recent work that we published last year on an S&P workshop, at least the core idea of it. Because you can also hide data in the IoT or in cyber-physical systems. And the question is, why would you do that? Well, it's not the case that many people will look for a secret message in a building automation system or something. So why not use it for storing secret data? Also, CPS systems are not always so secure, as you know, and while they are carried around with the people, they are maybe not as well protected by data leakage protection methods, etc. So you can bypass traditional filter systems using the IoT network components. How can we do this? Well, there are several ways. One is that we utilize unused registers of CPS components that work quite well and fast. Another one is shown in the picture. We modify actuators. So let's say you have a heater, and you can select different heating values for your heater, and you learn how the building functions and which values are usually configured for which device. Then you know, okay, this heater is usually set to level 4.1 out of 5 or something. What you can do is changing the value slightly to 4.0 or 4.2, and then this can represent your hidden data bit. If you combine multiple devices, you can store more bits. And however, it's problematic because CPS status device components usually change their status a lot. So you have to be adaptive with your hiding technique. That means you constantly have to monitor it. You have to apply redundancy so that your data is stored not just once, but multiple times. And but it works fine. However, so far we could only store about 350 bits to 1.5 kilobits in a smart building of a medium size. Or, in other words, we need about 30 actors just to store AES key of 128 bits size. And here's my third and last challenge for you. Store more data in a CPS and try other CPS types. We just focused on smart buildings. Actually, the temperature sensor that we also utilized could be deployed in other CPS environments as well, but maybe it works with wearables or healthcare equipment or whatever. So be creative, store the data, show that more data than just a few kilobytes can be stored, and then the application domain may become much more interesting. Okay, here are the references. Most of my publications are on the link below, and you can just download them from there. That's it. I have 1 minute left. Thank you, and maybe you have questions.
Questions, anybody?
Hi, regarding challenge 1, is there already a pattern that detects messages which has different types of resource allocation? For instance, if you can trigger messages to a system which up the CPU cycles on an average to 90% or not?
Yes, that's the how did we call it? Well, there's one technique developed by Stephen Murdoch that utilizes corkscrew of a system, and you influence the temperature of the system using many requests that you send to it, and then the recipient can reduce the sender's information in that sense. So yes, there's a pattern.
Then I'll keep working on challenge 1. Well,
there's lots of stuff you can do, and there are just, I think, 2 techniques that represent that pattern. So there's room for more.
Okay, last question.
So there's a slight overlap between certain attacks on crypto and steganography, like the crime attack, compression ratio, information leak made easy. Would that classify in your classifications of steganography attacks or not?
So the thing is that there are overlappings in the terminology. That's true. In cryptography, you usually have side channel attacks. And side channels are covert channels that are sending without intention in that sense. So it's a subtype of covert channel in the classical taxonomy.
Thanks.
Okay, thanks very much. Please give a hand for Steffen.